function of hemoglobin today.
There's another box.
Yeah, these two will be okay, I guess. So let's talk about hemoglobin in general. So we know what hemoglobin's main function is. It's to carry gas. Okay, that's what it does. It carries oxygen, and then it plays a role in helping us get rid of carbon dioxide. That's its main function. Okay. Without that, there's no reason to even have hemoglobin. But one of the things we're going to talk about is it's called the hemoglobin. I can't spell today. Hemoglobin dissociation curve. I think that's how it's spelled. Okay. So basically, you have a graph. Okay. Up this side, you have saturation. Okay. Of hemoglobin with oxygen. So what does that mean? What did I tell you guys saturation means? The other day we talked a little bit about it. I said, have you ever heard the word saturation? And some of y'all said no. Saturation essentially means that it's full. When you have something that's saturated, you might hear old people talk about, well, if it rains tomorrow, it's going to flood because the ground's saturated with water. You know what I mean? That kind of thing. So that means it's got more water than it can hold, or it's full of something. So in our case, how many oxygen molecules causes a hemoglobin molecule to be saturated? 4. Because we know we've got our little saturate or bonds like that. So that means we have an oxygen here. So we have an O2 here, an O2 here, and an O2 here, and an O2 here. Okay? So that means it's saturated. It has full capacity to carry oxygen. Okay? So that's what we're talking about here. So we have a 0 on both sides. And then we have a mark at like 20, mark at 40, 60, 80, and 100. Okay? And that's percentage. Alright? That's saturated. Percent saturated. Got my percent there. Okay? Then on this side of our curve, we have the partial pressure of O2 in millimeters mercury. Oops. Okay? Here. And it goes also 20, 40, 60, 80, and 100. Okay? Because that's about all we need. Alright? So what you're going to see is you're going to see something that kind of looks like this. If we plotted it on a graph based off of the amount of hemoglobin we have something that kind of looks similar to this. And it's actually called an S curve. Okay, it's a sigmoid. Okay, that's normal. Okay, so we're going to talk about this thing in just a minute. It's called P50. P50 is when 50% of all hemoglobin is saturated. Okay? So this number is very important for us. Okay? So when we're looking at that P50 curve, okay, it's going to be about right here. Okay? All right? So basically, 50% is going to be right here, right? That's going to be about 50%. I'm not measuring it exactly, but that's pretty freaking close, okay? So what we want it to do is we want it to come out and be equal to about 25 millimeters mercury, okay? At 25 millimeters mercury, so from here up, these two need to be even with each other. Does that make sense? So right there is where P50 is for us, okay? So 25 millimeters mercury of O2, we should have 50%, all right? That's normal, that's what we want, okay? But sometimes things happen in our body, okay? We can get, all right, now I'm going to say pH, but your book says hydrogen ion. So let's talk about that for just a minute, okay? So in chemistry, you guys should have heard a statement about a proton donor or a proton acceptor. Is that right? Or is it ACC? ACC?
ACC-EPTOR.
Okay. Acceptor. Alright? So what does that mean to you guys, chemistry-wise? What does it mean when I talk about a proton donor and a proton acceptor?
The donor gives the proton and then the acceptor takes.
Nope. Well, yeah. But what's the proton? What's the only atom in our whole universe is considered to be just a proton? Anybody know? Huh? Somebody about said it. I heard it. Hydrogen. That's right. Because look, hydrogen's a really weird element. It's a gas. Okay? But we know that its atomic number is 1. Right? So on the periodic table, every atom on the periodic table is neutral. Okay? So that means if we pulled up its nucleus, it would have 1 proton, and on its outer shell, it's going to have 1 electron, right? Has to be neutral, okay? But what happens a lot of times is because it has that one little lone electron, that electron gets stripped off very easily, and it gives it up. So what's left is its nucleus with 1 proton. So now, instead of it being hydrogen, it's become an ion, which is hydrogen plus. Okay? So a lot of times when you, or all the time, when you see it talking about a proton donor and a proton acceptor, it's talking about that compound or that chemical is able to grab a hydrogen ion. Okay? So, what is the definition of pH?
The percent hydrogen.
Percent hydrogen, what?
So,
Percent hydrogen, what? What is this? What did I just say this is? Hydrogen ion, right?
oh, okay.
It is the percent hydrogen ion, okay? So, let me ask you a critical question. pH is 0 to 14 with 7 being in the middle, okay? So, if I go this direction, what happens to my pH? It's acidic, so it does what? Goes up or down? It goes down because I'm going from 7 to 0. Now, what happens to my percent hydrogen ion? Go up or down? Up. That's exactly right. So if I have somebody that has a 1 pH, all right, it's going to be 70 times more hydrogen ions than if I was looking at water at 7. Does that make sense? Okay? All right? Because it actually goes down like tenfold each number it drops. Okay? All right? Does that make sense to you? All right? Now, if we go up, though, what's happening to our percent hydrogen? It actually is going down. And in this case, what do we usually see an increase of? The closer we get here, what do we see an increase of? Hydroxide. Okay?
Hydroxide.
Alkalinity is right. That is the correct term. But the reason it does that is because there's a polyatomic anion or polyatomic ion called hydroxide, which is negatively charged. Okay? Where does that come from? Because 7 is neutral, H2O, right? Water gets broken down, it is hydrogen and hydroxide. But because this is a single unit and this is a single unit, that's the reason we say they're equal to each other. Does that make sense to you? So that's the reason 7 pH is neutral, okay? But as you go up this way, this decreases and this increases, hydroxide, okay? And then right the opposite is you go the opposite direction. Hydrogen increases, hydroxide decreases, okay?
Can I take a picture before?
Take a picture.
Not with
Can I
you.
pose?
I don't want you in it.
That hurts my feelings.
Good.
But I don't have no feelings, so it doesn't matter, okay?
Oh, I didn't mean to do the 5.
Dang, girl!
Sorry.
Okay? Alright, another thing that we look at is temperature, okay? And then there's this thing, okay, so last couple of chapters ago, when we were talking about the red cell, okay? 2, 3, BPG, I think that's right. Let me make sure before I tell you this. Yeah, BPG. Is that what I got? BPG. 2, 3, BPG. Okay, so think back to when we were talking about the cell's respiration, cellular respiration. We talked about how that in the red blood cell, it goes through anaerobic glycolysis. Remember us talking about that? So we burn glucose anaerobically instead of aerobically. Remember that? Okay? So one of those, there was like 3 different cycles. The Embden-Meyerhof. There was the hexo-monophosphate shunt. And then there's one more, and I can't remember what it is. Doesn't matter. Okay? But one of the byproducts of that respiration is this 2,3-BPG. Okay? Alright, so let me see if I can make this make sense to you. Alright? This plays a role in the affinity of oxygen. Okay, so remember the other day I told you what affinity means, right? Affinity, I have an affinity for my wife. I've always been attracted to her, but I also have avidity for her because she's my sugar mama, and I don't want to do nothing to mess that up, right? She makes lots of money, so I want to hold on to that. You remember me talking about that? Okay. So 2,3-BPG byproduct plays a big role in the affinity of oxygen and the hemoglobin molecule. Okay. All right. So if I see an increase in this, it basically makes it so that I don't bind oxygen as good, okay? My affinity, my affinity is actually increased, but so my avidity is also, okay? So let me ask you, is that a good thing or a bad thing?
Bad.
It's bad, okay? Yes, I'm grabbing oxygen like I need to, but if my avidity's high, what's it going to do when it gets to the capillaries? It won't release it. And so CO2 begins to build up in our tissue, okay? Because really what we need it to do is to have an affinity for it for a little while, but a little lower affinity so that it can also give it up. Does that make sense? Okay.
So it's increased affinity and also increased avidity.
That's it. Anytime your affinity is increased, so is your avidity. Okay? All right? So, what happens is we get shifts to the right or to the left. Okay? So what happens is on page 85 of your book, okay, you can see what happens. All right? So, we can have either increased or decreased of these same things. So CO2 decreased pH. Well, I should say in this case, it's decreased hydrogen ions. That way it makes sense. Because what really happens to the pH, it goes up. Correct? Because we have decrease in the hydrogen ion. Does that make sense? So I'm going to leave it hydrogen ion like what's in your book. All right, decrease temp and decrease 2,3 BPG. Okay? All right? So what happens is, if I get an increase, okay? If I get an increase of these, I get a right shift. Okay? So instead of my curve coming here, it shifts and does this. Well, crap.
You should do different colors.
That's what I was planning on doing. That's the reason I got the chalk out. But I'm stupid. Okay?
Which one is it?
So this is going to be my right. So my right shift is when I have an increase in all of these things. Okay? So essentially what happens, guys, if I'm having an increase in 2,3 BPG, what's probably happening in my tissue?
CO2 buildup.
Well, yeah, it is going to be CO2, but what's causing it to start with? Increased what? What did I tell you this is a byproduct of? Glycolysis,
Okay.
right? So breakdown of glucose, so respiration, right? So what's happening probably in my body?
It is.
My tissue is being what?
It's being. I don't know.
It's being overworked.
Yeah.
Okay? So in other words, exercise, I went into sepsis, like in my body, like I've got a really, really bad infection, so it's causing problems with my tissue, okay? All right? So those things are going to lead, so look what happens. If we're here normally and we shift to the right, what happens in my affinity on this side?
Decreased.
No, you're right. It is decreased. Okay? Because look, right here's P50 at 25 millimeters mercury. Look where P50 is now. Closer to 40. Right? So in that case, that means that my affinity for oxygen is not as strong. So therefore, I'm not grabbing oxygen as quickly as I normally would. Okay? So then write the opposite. I get a left shift when I have decreases in these. So what you see is you see the line coming here. Now this case, we have an increase in affinity. As soon as oxygen comes available, I grab a hold of it. Okay? But the problem is, not only am I grabbing it sooner, I'm also doing what up here? I'm holding on to it longer also. Does that make sense? Okay? So that's not a good thing for me, for my body, because yes, I may be getting it saturated really, really quick, but I'm also not turning it loose really, really quick. So I'm holding on to it, so therefore CO2 is going to build up in my tissue. Okay? All right, any questions about this? All right? I spent a lot of time on this today because you will see it again later on. When we start talking about this in clinical chemistry in the fall, you'll also see this again. Okay? So just kind of be aware of what's going on here. Okay? Questions about that, guys? All right. So, since we're talking about affinity, let's talk about this real quick. And this, I'm getting ahead of myself, so you may can change slides if you want to. There's a slide in there that talks about tense state and relaxed state. Okay? All right. So,
It's 448.
is it in there? It should be in there. It should be one of the slides. Okay? All right. So, what does that mean? All right. So, we talked about how that we have our well, let's not do this. Let's do it in white. All right. So, look. So, we have our hemoglobin molecule. and we have these bridges that bond, okay? Two together. We'll keep that tetrad, okay? There's two dimers added together makes a tetramer, okay? So you got beta 1, beta 2, alpha 1, alpha 2, okay? 2 alpha, 2 beta, right? Okay? So inside here, we know that we have the heme ring, okay? We're just going to call it the ring right now, okay? And inside this ring is where we want our oxygen to get to, okay? So we've got oxygen hanging out here, waiting to get in, okay? The problem is when hemoglobin, and let's go ahead and talk about that. Let's talk about two forms of hemoglobin. I think it's on the next one, but we're going to talk about it now. Oxyhemoglobin and deoxyhemoglobin. Oops. All right. So oxyhemoglobin is hemoglobin. Oops. Bound with oxygen. Deoxy, no oxygen. Makes sense, right? Deoxy, okay, taking off. So no oxygen, okay, so just hemoglobin without oxygen. All right, so most deoxyhemoglobin is in the T state. That means it's in a tense state. So what happens is, if you'll look at it, is hemoglobin is like this, pulled in tight, like I'm holding on to my hands, okay? All those atom bonds, sulfur bonds, salt bonds, all that stuff's really, 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 really tight, okay? Now, hemoglobin has an affinity for oxygen all the time. It may be low or it may be high, but it still has an affinity for it, okay? Because iron, just like if I left a piece of iron laying outside, it's going to do what? Rust. Why is it rusting? Because it's oxidizing. Why? Because iron has an affinity for oxygen, okay? No matter what. It's just a natural attraction to those atoms, okay? So anytime iron gets close to oxygen, it does want to bind it, okay? The problem is, oxygen's got to get attached to it, okay? All right? So what really happens molecularly, you know, we talked about that protoporphyrin, I think that's how you spell it, ring, that we talked about earlier, okay? So it's not even with it. The iron molecule actually sticks out from it a little bit, okay? It's not right even with that plane, okay? So what happens is, though, when it gets in proximity to oxygen, there is that attraction for it. And when it has that attraction, it actually gets oxidized, and this bond gets shortened, okay? So now it moves in a little closer, and it's about even to that end or the plane of that protoporphyrin ring, okay? So then when it bonds with the O2 there, that tension, okay, begins to loosen it up a little bit, okay? Then what happens is when it loosens, it gives way for another oxygen molecule to grab a hold of it, okay, to bond, all right? When it does that, these bonds are almost completely broken. Those salt bonds that are part of the molecule get broken, all right? So when it does that, instead of being like this, now it's like this. It's still connected, but it kind of opens up. And when it opens up, it gives way for these to jump on really, really quick, okay? So the first O2 is still in the tense state. When we add the second O2, it begins to relax. But by the time the third and fourth are added, we're in that relaxed state. okay, has to be in that relaxed state, okay? Why is that important for us, okay? Because once it goes in the relaxed state, once it breaks those bonds with the addition of the second oxygen, then we lose some affinity, okay? It's going to bond, but they're not going to bond as strongly. So you have lower affinity, but you also have a decreased avidity, okay? So that way it's open, it's saying, when I get to the tissue, now I can give up that oxygen really, really quick, okay? Now, once we get into the capillaries and diffusion occurs, okay, we give up our oxygen, then we add, the bonds come back that were broken, we go to the tense state. All right, again, now we're at deoxyhemoglobin, okay? So deoxyhemoglobin is always in the T state, and oxyhemoglobin is always in the R state, okay? It's called a conformation. R conformation, T conformation, okay? All right, so now let's talk about carbon dioxide, all right? And just a little about, we're going to talk more about it, but I'm just going to mention it right here because this is a good place, okay? Carbon dioxide doesn't bond with heme, okay? Heme is there, but it never bonds with CO2, okay? So you remember what globin chains are made out of? What are globin chains made out of? Amino acids. Remember what I told you not to call your mama. Don't call your mama amino acids. She get mad at you, right? So amino acids. What's unique about amino acids is the chemicals themselves have a C terminal, which basically ends in a carbon atom. Okay, you know all living things have carbon, right? That's what makes an organic molecule organic. It contains carbon, okay? But they also have a nitrogen terminal, okay? It's known as the N terminal, okay? Every one of the amino acids that are in this thing have an N terminal. Some of them are free N terminals, meaning they don't have nothing bonded to them. So those N terminals is where some of the CO2 gets picked up, okay? And it's actually called carbamino hemoglobin at that point. And we'll talk about that a little later on, okay? All right, questions about function of hemoglobin? That part with the oxygen. Okay, yes, ma'am.
Can you just say that word again? I can't read.
Carb, like C-A-R-B, amino, hemoglobin. There's a whole nother little section on that in just a minute. On page, make sure I'm telling you right. Let's see. Carboxy. Make sure I'm spelling it correctly for you. Make sure. Let's see. Yeah. Carb amino hemoglobin.
I found it on slide.
You find it? Okay.
It's on
Cool.
slide 152.
Okay, cool. All right. So, any questions about hemoglobin, oxygen affinity, and that kind of thing? Okay. All right. Well, we covered several slides right there in that little thing. Okay. Y'all do understand that that's what a PowerPoint's for, right? It's not like it's supposed to be every word I say. It's supposed to be it's basically a tool to prompt me to tell you something. Does that make sense? Okay. All right. So oxyhemoglobin, hemoglobin with bound oxygen, deoxy without oxygen. And then we talked about oxygen affinity. You guys know what that is at this point, I hope. Okay. So increased oxygen affinity, high oxygen affinity, bind it more avidly, okay, which is avidity. Does not readily release it, which is not a good thing, okay. So decreased affinity, it has low attraction, but it also has low affinity. Okay, so this is what we're talking about with the T state and the relaxed state, R state there. Go ahead and you can look over that. P50. I put 25, I'm sorry. It's 26 actually, but you know, 25, 26. It says about 26. That's what that little squiggly means. So probably at 25 it would do the same thing. Okay. All right. Questions about that? Anything?
What's MMHG?
What?
MMHG.
Where you see that at? Oh, millimeters mercury.
What's that?
Okay. So, give you a little history. Okay. How many of you watch James Spann? I like James. James is the man, right? James Spann is the man. Okay. So every time we have a tornado in Alabama, okay, puts all the numbers up there, the weird numbers. And a lot of times he'll talk about barometric pressure. Y'all remember that? Okay? So barometric pressure is actually really cool. Right? So chemistry, what is mercury? What's unique about mercury?
That's a liquid and a solid.
It's a liquid and no.
It's a liquid metal.
It's a liquid metal. It's the only metal classified as a metal that at room temperature is in a liquid state. Okay? So what people figured out, and you know, it took a lot of years to do this, but they did figure this out, that you can measure pressure. Okay, first of all, what's pressure? What's pressure? Huh? Y'all know what pressure is? Y'all want to talk gas laws in chemistry? So I missed that day? Y'all skipped that?
Well, I'm in chemistry right now, so I'm
Oh, okay. So you got there yet. Some of you guys that have taken chemistry, what is pressure? What does pressure mean? Say it loud.
The force that's started on the container.
That's exactly right. That it's basically pressure is the force that is exerted on the container. What's the exertion being caused by? Maybe. What phase of matter are we talking about most of the time? Gas. Okay. So we breathe in air, right? Air is a gas, right? So our air contains nitrogen, contains oxygen, contains CO2, contains a little bit of helium. That's about it. You can get on down. There's things like neon and krypton and radon and all these other gases too, but these are the most common gases that are in the air you breathe. Okay? All right, so we know that pressure has to be 100%, right? Okay? So let me ask you, if every one of these is contributing to the 100% pressure, how do we know which one is which? Or how much each one is giving us? Yeah. But we know that just one of these is not contributing to the 100%, don't we? Because we know it's a mixture. All right? So the term that we use is partial. Partial pressure. Okay? Because we know that hydrogen is putting a partial pressure on the 100%. We know that CO2 is, we know that oxygen is, and we know that nitrogen is, and of course those other weird ones that we don't really think about. Okay? So what we do is we say PO2 and PCO2, because those are the two that are important to us in our body, right? We don't really care about the nitrogen that much. We do, but not at this point, okay? These two are important to us. So we put a P in front of them as partial pressure, okay? So those are important to us, all right? So to get back to her question, so back in the day, we know that air has a pressure, okay? So they had to figure out a way to measure it. And essentially what they did is they created a barometer. And they basically put a pool of mercury, and then they fixed a graduated pipette on it and measured it in millimeters. Okay? So what their theory is that when air pushes on mercury as a metal, pressure you push down on something, what's it got to do? It's got to go somewhere, right? And so their theory is it would shoot up that graduated cylinder. And so essentially that's what it is. They look and see where it comes to on the barometer. So let's say that that's 50 millimeters of mercury. Got to know that?
No.
Who wants to be a millionaire question right there? Falling free. Call Mr. Thomas.
What is the alveolar capillary membrane?
Those are the alveoli, or the little sacs in your lungs that do gas exchange.
Okay.
It's where when we suck in oxygen, breathe out CO2, that's all taking place right there. Okay, that's where we're fixing to get, aren't we? Are we fixing to get on that?
I don't know.
We're going to talk about the lungs right here, aren't we? Let's say something about the lungs. Did I miss that slide? Where was that slide at?
I don't know. This
Well,
is my
right there.
notes from my
Oh,
photo.
in your notes.
This is my notes from my
It's
photo.
Oh,
on the-
okay.
It's on the screen.
Is it on the screen? Yeah, that's what we want to talk about right there.
Here's a little-
What we're going to talk about, Kara's getting ahead of us. All right, so let's talk about CO2. All right, so we talked about oxygen and how oxygen gets to our blood, into our blood by hemoglobin. That's the transporter, okay? But, so go back to phlebotomy, right? And we talked about how we got arteries, arterioles, capillaries. Oops. Maybe 2 L's. Maybe there's only 1 P. Capillaries. Yeah, that looks better. Venules. And then we got veins. Remember that? Okay. The important thing is right there. Why is that important?
It carries the CO2.
Because that's where what occurs. Yeah, you're right. I mean, well, it doesn't really carry CO2, but that's where CO2 is concentrated. So, what happens in capillaries? What's their main function?
Gas exchange.
Gas exchange. Attaboy. Okay? So remember from phlebotomy, I told you this, guys. I said, okay, if I bought a bottle of perfume and I set it on the table here, okay, and I popped the lid and I stuck my nose down at it, smell like crap, right? But I can still smell it, right? Really, 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 really concentrated, I can smell it, okay? If I stand up and then walk back there to the back corner, am I going to smell it? No, I'm not. If I keep staying in that corner, am I going to smell it?
Yes.
Yes. Why?
Diffusion.
Diffusion. Because what's the definition of diffusion?
Highest concentration to lowest concentration.
High concentration to low concentration. So movement of particles from high concentration to low concentration. So what does that mean? That means equilibrium. Everything in our body wants to be at equilibrium if it can. Okay? So here, high concentration. Back there, low concentration. Those atoms or those molecules, they want to be equal. They don't want to be hanging out all bunched up together. Excuse me. This soft dust is getting me. Okay? So, let me ask you a question. I done asked you this in phlebotomy, but I know y'all forgot it. Okay? Blue whale versus a shrew.
It's a shrew.
Little bitty mammal about this big. It's a little mole-like thing. Lives in the ground. little shrews, okay, about this big, okay? Blue whale, right? Little shrew. Are their cells the same size?
Yeah.
Yeah.
Who says yes? Who says no? Yes is right. They are exactly the same. Why? Because if I have cells that are this big, diffusion doesn't work real well over a long distance. But it does work real well at a short distance because it doesn't require what? Any, even more important, oxygen. What do we always want to conserve in our body if we can? Energy. Exactly right. Diffusion is a passive thing. It just works because atoms don't like to be bunched up together, so it goes out. Okay? So, but it works well in small distances. All right? So your capillaries that branch off, if we pull them up and look at them, are only like 1 or 2 cells thick. Distance between them and the lumen. Okay? Okay, y'all remember the lumen? What's the lumen? This is the lumen. That's the hole where the blood's flowing is your lumen. You remember we talked about this is the endothelium, the cells. We talked about the difference between arteries and veins, the thicknesses of them. Okay? Capillaries is only like 1 or 2 cells thick. Okay? The reason it is because of diffusion. Okay? So let's talk about diffusion. Alright? So, over here in my arteries, I have red blood cells that have lots of what?
Oxygen.
Oxygen, right? Because that's what arterial blood is. Arterial blood is oxygenated blood, correct? Okay? So lots of oxygen saturation there, okay? Over here, I have tissue. Right? Tissue. What's happening in my tissue all the time?
Gas exchange.
Gas exchange? No. If I want to work out, I don't ever want to work out, but if I do, what I got to do? What's the muscles got to do?
Move.
Got to create what?
Lactic acid.
Energy, right? How do they make energy? Make it, tell them.
ATP
ATP. How do we make ATP?
for anaerobic respiration
Cellular respiration. That girls. Basically glycolysis. We're taking glucose, breaking it down into either pyruvate or lactate. Okay? Making ATP, right? What's a byproduct of cellular respiration?
Carbon dioxide.
CO2. Okay? Think back to your childhood,
You can't see that.
3rd grade. Okay, we'll do something different then.
Yeah, we can see that.
We'll do CO2. Okay, so think back to 3rd grade. You were taught CO2 plus oxygen gives us C6H12O6 plus oxygen. Oh, I'm sorry. Screwed up. H2O, right? CO2 plus H2O gives us glucose and oxygen. What is this? Starts with a P. Photosynthesis, very good. Then we said the opposite of photosynthesis is C6H12O6 plus oxygen gives us CO2 plus water plus energy. Okay, and then you would have the energy right here too. Right with the sun. You remember that? Guess what? This is the circle of life. Really. Not Zumba, Zimba, whatever the little dude's lion's name was. This is the circle of life. Okay? Does that make sense? Glucose gives off CO2, oxygen's needed. Okay, so we get Lots of CO2 in our tissues, right? Okay? So what happens is, our little red cells are coming in here. As soon as they hit those capillaries, what is the difference in concentration? How much CO2 are in our red cells? How much CO2 is in our red cells at this point? Say it loud and proud, baby. None! Absolutely none. Because what did we do? This is arterial blood. So this is coming from our lungs, right? Full of oxygen, no CO2. So as soon as them red cells hit this area, what's going to happen to the oxygen? We got any oxygen in here? In our tissue? Any oxygen? No, because what did we do? Right? We used it all up. So there's no oxygen here, so what's the oxygen going to automatically do? Going to shoot out of those cells because of low oxygen levels. Okay? What was inside the red cells? Any CO2? No. So what's it going to do?
Pick up CO2.
Like that. And then some of it will get in the plasma also and go this way. But a lot of it's picked up by the hemoglobin and also picked up and put inside the red cell. Okay? That's gas diffusion. That's gas exchange right there in a nutshell. Okay? So where does CO2 go? Okay? 3 ways our body can get rid of CO2. Okay? First thing, it can dissolution in the plasma. What does that mean? Does it stay a gas? Huh? No. It kind of dissolves into the plasma and then it's just taken out. Okay? So, when you do start working in the lab, we do CMPs and BMPs. Okay? Complete metabolic profile, basic metabolic profile. Guess what all of them have? A CO2 level. Okay? Whether we use serum or plasma, excuse me, we still pick up CO2 levels. Okay? So we're always going to have some CO2 in our venous blood. Alright? Because at this point, what is blood in the veins? What kind of blood is it? Deoxygenated blood. Right? Because in the arteries, it's oxygenated. Hit the capillaries, we exchange gases, send all the oxygen out, grab CO2, send it off. So it's actually called deoxygenated blood. Okay? So now it's full of CO2. Alright, the next thing that it can do is it can dissolve in the plasma, or it can bind old. Writing too much today, guys. Alright, so CO2 plus water with Ca, okay? Ca is an enzyme, okay? Carbonic anhydrase, is that right? Is it in there?
It says carbonic acid.
I know, but does it talk about the enzyme? Ca?
I don't think so. I never saw
Okay, it may not. So let me make sure I'm telling you what it's called. I'm pretty sure that's what it's called. Yes, carbonic anhydrase. Okay, Ca stands for carbonic anhydrase. Okay, synase, so it's a what? Enzyme. Okay? Anhydrase basically means it's going to transfer a hydrogen ion. Okay? So what we end up with, H2CO3. Okay? Which is known as carbonic acid. Okay? Can form carbonic acid. Alright? Then, carbonic acid is broken down into a hydrogen ion plus bicarb. Okay? This is bicarbonate. Okay? This is one of the most important buffering systems of our body. That's the reason hemoglobin in red cells is a huge buffer system for our pH. Okay? So I've kind of talked a little bit about this in 131. So our blood pH likes to be between 7.35 and 7.45. Okay? Not quite acid, not quite basic, just kind of in the middle. Not exactly neutral, but it's close to being neutral. Okay? Anything that goes below this, we die. If it goes above this, we die. Okay? So, what keeps me from making my pH drop when I drink a Coke? This. Okay? Because I put all those hydrogen ions into my body, okay? And then this hydrogen ion will actually go out through our urine, usually. Okay? Back into the plasma and go out through our urine. Okay? So, dissolve in the plasma. Oh, let me tell you this too. This is happening in the RBC. Okay? I don't know if I told you that or not. Okay? So this is happening. So a while ago when I drew that picture, carbon dioxide went inside the red cells and changed places with oxygen. This is what's happening. Okay? CO2 bonds with water in the presence of carbonic anhydrase enzyme to form carbonic acid. Okay? Then carbonic acid is broken down into a hydrogen ion plus bicarbonate.
And the hydrogen ion is the waste?
Yes, it'll be a waste. And bicarb won't stay in the red cell long. It'll actually go out also. But it floats around in the plasma. I'm not going to ask you that, so don't worry about it. Okay? This is what I want you to know. This is happening in the red cell. Forms carbonic acid with the help of carbonic anhydrase enzyme. Okay, if this is not there, it can't take place, can't happen. Okay? Carbonic acid is broken down into bicarb and hydrogen, a proton. Okay?
What does it say above that ink?
Buffer,
No, not that one. No, keep going. That
urine. Okay? Or we can get what we talked about a while ago. The carbamino hemoglobin. Remember what I told you that one a while ago? Carbon dioxide can bond to the hemoglobin molecule on those end terminals of the amino acids. And then it can be taken to the lungs and dispelled when oxygen is brought back in. Does that make sense? Okay. Questions? Okay, very good. All right, two things. Extravascular, intravascular hemolysis. What time are we getting to?
It is 11:41.
All right, we got plenty of time to finish. Okay? Not going to spend a lot of time on this because we're going to extravascular hemolysis versus intravascular hemolysis. Okay, so this is very, very important to us. Okay, all right. So, extravascular, of course, means where? Spleen, bone marrow, and liver. Yes. Okay. So this is the most efficient pathway that we want to do. Okay, always. All right. When we do it this way, we're able to recycle the amino acids from the globin chains, and we're also able to recycle the iron. All right? The only thing that's really ever going to be broken down once we basically try to destroy hemoglobin is the heme molecule. Okay? The other ones are broken down, but they're saved. Okay? So, heme is broken down by the macrophages. Okay? Heme, iron, and globin. Okay, globin, of course, is a polypeptide chain. So basically what happens, globin gets broken down into its primary state. So it gets broken down from quaternary, tertiary, secondary, and back into primary. So it's basically just a bunch of little chains of amino acids. Okay? All right. Iron and globin are conserved and reused. Okay, here's some terms you need to know. Iron can be stored as ferritin or hemosiderin. Okay? Both of these are usually stored in the bone marrow. So like when we do our iron stains, that's what we're staining for. We're looking for stores of ferritin and hemosiderin. Okay? So if I ask you, what's two forms of iron storage, you will tell me ferritin and hemosiderin. Okay? All right, now this goes for our entire body all the time. I know we're talking about hemoglobin, but later on when we start talking about iron deficiency anemia, these terms are going to pop back up. Okay? So I want you to make sure you know these. All right? So, released to a transport protein called transferrin. This is another term that you need to know. Transferrin is a weird little dude. Okay? Kind of shaped like this. Alright? And it has two spots that it can bind iron. Okay? So each transferrin molecule can carry two iron molecules with it. Okay? All the time. We have saturated and unsaturated transferrin. Okay? We actually call it UIBC and TIBC. Total iron binding capacity, and UIBC, unbound iron capacity. Okay? So like TIBC is saturated. It's got two on it. UIBC, it would just have one or none. Either one. Okay? Okay? Alright? So, responsible for 80% of the iron in our transferrin pool. Okay? Globin is broken down, stored in the amino acid pool in the liver. Alright, so let's talk about heme. That's the important one here. Okay? Alright, it's all written down, but this is what I want you to look at, is the flow chart. Okay? So, spleen, liver, bone marrow, macrophage. Okay? Breaks hemoglobin down into heme plus globin. Okay? Alright? Globin gets broken down and sent to the liver to be stored. Okay? In our amino acid pool. Alright? You with me? Heme is broken down into three things. Okay? The first thing is known as biliverdin. Okay? You need to know that term. Biliverdin. Plus carbon monoxide. Okay? CO is carbon monoxide. It's a gas. Okay? Plus iron. Okay? Then iron is picked up by transferrin and sent to the bone marrow. Okay? Where it is stored as ferritin or hemosiderin. All right? You with me so far? Okay? Carbon monoxide is sent to the lungs to be expelled. We're going to talk about CO, carbon monoxide poisoning in just a minute. Okay, carboxyhemoglobin. Okay? CO is carbon monoxide. It's going to go to the lungs and be expelled.
Okay.
We're going to talk about carbon monoxide in just a minute, later on. Okay? Biliverdin in the blood, okay, goes to the kidney or to the liver to be turned into bilirubin. Okay? Through enzymatic reactions, biliverdin is turned into bilirubin. That's all I want you to know right there. Okay? Biliverdin turned to bilirubin. This happens in the plasma. Okay? While bilirubin, when bilirubin is formed in the plasma, it binds with a protein called albumin. Okay? Once these are bound, it is known as unconjugated bilirubin. Okay? This is also known, write this down, it's also known as indirect bilirubin. Okay? Bilirubin plus albumin is known as unconjugated or indirect bilirubin. Okay? You with me so far? I need to slow down a little bit.
A little. Indirect.
Indirect bilirubin, or unconjugated.
And this is all in the liver still?
This is all in the plasma right now.
Plasma.
Okay, in the plasma. This is happening in the plasma. Enzymes in the plasma are breaking biliverdin down into bilirubin. Bilirubin then binds with albumin, which is the protein that makes up most of your total protein in your plasma. Albumin is a transport protein, what we call a transport. It does a lot of transporting chemicals in our body. Okay?
Did you say protein?
It's a transport protein. Yes, albumin is. All right? Then once it is unconjugated, or known as indirect bilirubin, so it's bound to albumin, it then goes to the liver. Okay? In the liver, the hepatocytes inside the liver, through enzymatic reactions, they basically change it to conjugated. All right? They change the form to bilirubin diglucuronide. Glucuronide. Okay? Look, it's direct bilirubin is all I want you to know. It's known as direct bilirubin at this point. Okay? What makes it unique, once it gets this glucuronide added to it, it becomes water soluble. Okay? Here it's not. It is not water soluble as indirect bilirubin. Okay? But once it becomes conjugated, direct bilirubin, it is water soluble. So now it's going to go to the gallbladder, into the bile duct of the small intestine, okay, and to the gallbladder, where it is broken down into urobilinogen. Urobilinogen is then in the blood, placed back into the blood. Then it goes to the kidneys as urobilinogen out of urine. Okay? Now, up here in the stool, okay, it's going to go in as urobilinogen, and it's going to go out as urobilinogen or stercobilinogen. All right? Urobilinogen, and this is going to sound gross, but this is just what it is. This is what makes your poop brown. Okay? Later on, we'll talk about when there's a problem with extravascular hemolysis and it's not working properly, people can have what we call chalky stools. They turn white. Okay? If you see that, there's a problem with the breakdown of urobilinogen. It's not being broken down, so their stool's not turning brown. Yes, ma'am?
So what happens when it's green?
Well, that's usually like dyes and stuff, foods you eat. Like purple dyes will do that. You drink like purple Kool-Aid or grape or something, your poop will be green. Okay? But that's all like dyes, pigments and stuff that causes it. But this is just normal poop. Your normal poop stool is brown because of urobilinogen. Urobilinogen is a byproduct of heme breakdown. Okay?
What if you don't have a gallbladder?
Then they dumped it straight back into your small intestine. Your liver dumps it straight back into your small intestine, and it goes out as urobilinogen. Okay? Your liver actually does the conjugating in the thing. So your gallbladder is really not doing anything except being a transport medium with the bile being produced. Okay? But if they did, when they took out your gallbladder, they rerouted all your stuff to your small intestine. And so it's dumping stuff into your small intestine, which is what you want it to do in your colon. Okay? This is in your book. You need to be familiar with this. All right? Bilirubin. Increases in bilirubin means you also have increased extravascular hemolysis. Okay? So like when babies get jaundiced, the reason they're getting jaundiced is because they're popping red cells so fast, their little liver can't produce enough. It can't dump it enough. And so the bilirubin gets put into their tissue instead of going out through their gallbladder and urobilinogen like they're supposed to. Okay? Listen to me. Bilirubin is toxic to us. Okay? If we can't break down bilirubin, we will eventually die. Okay? So it's a very important thing for babies. All right? And we'll talk more about that in chemistry, but this is important. Okay? All right. Questions about that? All right? Intravascular. So this is happening inside the vessels. Okay? Inside our vessels. Okay? All right? So, Inside the vessel, it happens a little different. Okay, not much difference, but a little bit different. Okay, so in our plasma, we have a protein that is called haptoglobin. Okay, when hemoglobin or when cells break down, haptoglobin binds free hemoglobin. Okay, that haptoglobin, then hemoglobin plus haptoglobin goes to the liver. Okay, once it reaches the liver does the same job as it did for extravascular. Okay, so makes it bilirubin, urobilinogen, and those kind of things. Okay, all right. Problem is, okay, this is a problem. We don't have a lot of haptoglobin. So if you have a patient that has severe intravascular hemolysis, okay, so say I gave them the wrong blood type. That's usually the number one thing. I gave them the wrong blood type and they're having a transfusion reaction. Their body is popping all those cells so fast that haptoglobin can't hold on to it all. So you run out or deplete your haptoglobin level. Okay? So now you've got a bunch of free hemoglobin hanging out. So this is what gets weird. Okay? So it can do one of two things. It can just break down into the dimers, so an alpha and a beta together, okay? Or it can form met hemoglobin, okay? So essentially what happens, an enzyme oxidizes the iron, and it changes to iron 3, okay? So it's in the ferric state. Then it binds to hemoglobin, okay? Then the globin can be broken down, and then heme in the iron 3 state gets bound to what's called hemopexin. Okay? Hemopexin. Hemopexin plus heme can go to the liver and be broken down like normal hemoglobin. Or albumin can bind with it to form met heme. Okay, so up here heme and albumin can form. Then albumin gets broken off. Heme goes to the RE cells. These are reticular endothelial cells of the liver. And then they're broken down. Okay? All right, so go back up here to these dimers, okay? When you have 2 alpha, 2 beta dimers, because remember it's a tetramer, they get broken down by the kidney, okay? When they get broken down the kidney, the tubular reabsorption picks up like the amino acids, those kind of things, but iron goes out in the form of hemosiderin or hemoglobin and pushes it out. So you pee red, blood. Looks like blood, but it's really hemoglobin and not red cells. Okay? That makes sense? All right? Look, it's a flow chart. Just study it. Just read the chart, know what it is. Know that haptoglobin is a carrier, hemopexin is a carrier. Okay? Hemopexin carries met hemoglobin though. Okay? The heme that's in the iron 3 state, where haptoglobin still has regular heme with the iron 2. Okay, that's the 2 big differences in those 2. Okay? All right, questions? All right? We're not going to talk about nitric oxide. You guys can look at it. Nitric oxide is basically a vasodilator, okay? And it plays a role in basically it can help destroy hemoglobin if it's not in the right form, okay? All right, so I want to talk about a couple of acquired non-functional hemoglobins real quick, and then we'll be done. All right? When we have low oxygen, it's known as hypoxia. Okay? If you can't get oxygen to your body, it's called hypoxia. All right? Cyanosis is blue. If you get cyanotic, you get blue. I watch little kids all the time at the pool in the early summer or late in the afternoon, and their little lips will turn blue. The reason they're doing that is because their oxygen level is getting low. They're getting cyanotic, okay? So it's not a good thing. Bluish color skin, usually due to the presence of increased deoxyhemoglobin, all right? Met hemoglobin, this is the one you need to know about. Non-functional. So a while ago, we just mentioned met hemoglobin in intravascular destruction if haptoglobin gets done. But there are other things that can cause met hemoglobin. Okay? There is an inherited form and there is acquired forms. Okay? It doesn't matter which one it is, they all equal the same thing. Cyanosis. Because Met hemoglobin is essentially iron 3 binds with heme. Okay? When iron 3 binds with heme during that in the mitochondria when it's making that protoporphyrin ring, you're missing an enzyme that should convert it. That ferrochelatase is not there. So iron doesn't get broken down into iron 2 or oxidized to iron 2. So it stays in the iron 3 state. Iron 3 will not bind to oxygen. Okay? It just doesn't. So you don't get the oxygen carrying capability. So if you don't have oxygen, what happens? You die, right? Or at least turn blue. Okay? Because and let me make sure you understand this, not all of the hemoglobin is going to turn into methemoglobin. Most people do produce, especially in an acquired form. Okay, so like you got exposed to a chemical, a drug or something, and it just caused some of the hemoglobin to turn into methemoglobin. Okay, all right. So decreased oxygen carrying because it doesn't carry it at all. All right, normally less than 1.5% a day. Anything above about 5%, you're going to see the cyanosis. Okay? All right, congenital defects. So it's basically an enzyme's missing, the ferrochelatase. All right? When they have that, okay, cyanosis is observed at birth, and the met hemoglobin levels have reached 10 to 20%. Okay, you get home, Google, I actually got a picture. There's a family in Kentucky that are known as the Blue People of Kentucky. Okay? They have a congenital disorder. Okay? You want to really get right down to it, they're probably inbred somewhere along the way. Okay? Cousin married cousin or something. You know what I mean? I hate to say that, but that's true. That's just how it works. That's science. Okay? So these people like really, didn't want to be exposed to the public and all these other things. So, like, they were sick, they were blue, they were sick, whatever. So, a young doctor moves into town from, like, New York or somewhere, moved into this little town and figured out what was going on and gave them new methylene blue, okay? Like the stain, the dye that we use, the pigment. They actually have it in a tablet. You can take it in a tablet form. It corrects methemoglobinemia, okay? So, he gave them a pill and treated it. Does that make sense? So it is a genetically thing, but it's also a treatable thing because you basically, the new methylene blue kind of causes the oxidation. You can actually use vitamin C to do it too, ascorbic acid. Ascorbic acid is vitamin C. Okay? Yes?
Do they ever turn back normal?
Yes, they do. That's what I'm saying. It'll turn them back to normal. They'll lose the cyanosis. Okay? Now, once the new methylene blue wears off, they will start converting back to methemoglobin. So it'll be a lifetime of methylene blue that they'll have to take, or the vitamin C. Okay? No. So that tells you all that stuff right there. Another one, there's a picture, the blue family. So there's 3 or 4 of the people there that have it out of the family, 5 of them. The dad, of course, has it, so it's a genetic thing when the kids start getting it. Okay? So look at those. The one, sulfhemoglobin, I don't really care that much about. Basically, sulfur takes the place of the oxygen, so it can be toxic also. It's usually acquired, always acquired. So like people who live in big cities tend to have an increase in sulfhemoglobin because of the sulfur in the air, those kind of things. So just know what it is and be familiar with it. But the last one we want to talk about before we go is carboxyhemoglobin, okay? This one's important because you see this all the time. You can see this in the ER lots of times. Carboxy is when you get exposed to carbon monoxide. Okay, now a while ago we talked about that in intravascular hemolysis and even in extravascular, there's a little bit of CO that is produced normally in our body. But it goes to the lungs and gets, exchanged with oxygen, everything's okay. But when you stick your car exhaust into your car and try to kill yourself, this is what happens, okay? Carbon monoxide, all right? Hemoglobin has 200 times more affinity for CO than O2, okay? What does that mean? That means if carbon monoxide is in your body or in your area, it is going to grab hemoglobin before it will oxygen because it doesn't like oxygen as much. It thinks carbon monoxide is a prettier woman. You know what I mean? And it would rather hang on to her than oxygen. Does that make sense? Okay? So that's the reason it becomes really, really deadly. All right, so if you work in the lab, you go and draw blood on a patient who comes in comatose. You notice they have pink, rosy cheeks. You draw their blood and it comes out. You know you're in a vein, but it comes out cherry red. They have carbon monoxide poisoning. They need to be putting the oxygen to them. Okay? If not, they're going to die from it. Okay? So carbon monoxide is known as carboxyhemoglobin. Okay? When carbon monoxide forms with hemoglobin.
City dwellers.
Well, I mean, seriously. No, I mean, that's in the book. That's straight out of the book. City dwellers. People live in the city compared to people live in the country. They tend to have more carboxy and more sulfa hemoglobin than we do. Okay? All right. I believe that is it, guys. Questions about any of this stuff? I know it's a lot. But now that we've kind of established the basis, Wednesday we'll start talk. We'll take our test and we'll go ahead. Well, I tell you what, Wednesday we just won't start the next chapter. So we'll take our test and go home Wednesday. But what I was going to say, Monday, when we do come back and start lecture again, we'll start talking about abnormal stuff. So we're going to start talking about anemias
So
now.
we're not having a quiz on this stuff.
You will not have a quiz on this because you're taking a test tomorrow or Wednesday. Okay? And you guys know I'm not going to be here tomorrow, right?
We're not gonna be here.
Okay, so y'all have a couple of days break then.